I think this is the reason why it classifies it as zero helicity. This is actually the physical reason why this happens. While this one has been classified incorrectly, it is zero helicity, but it has been classified instead as positive helicity. And if you look at the graph from a visual perspective, it looks like a positive helicity indeed, because you have this cloud of points in the clockwise direction. So to conclude, the convolutional neural networks have outperformed the current state of the art by 20% without relying on very advanced techniques, actually, because I've just applied an existing pre-trained network, that is the GoogleNet network, without applying very innovative techniques, I have to say. And the pre-processing, I've observed that the pre-processing, that means the logarithmic scale for the colors and the cubic root, has contributed to an increase in the accuracy. In the previous experiments, I didn't obtain the same accuracy, and because I didn't add the pre-processing part. Instead, indeed, in the first presentation, the accuracy for the two classes case was about 80%, 84%. So there has been an increase with respect to that attempt of 10%. The accuracy increases as the number of samples increases, of course, but because of the computational resources that are quite limited, I cannot use all the computational resources all the time, of course. I have not generated a lot of data, but it is possible to generate them. It just takes more time. And the model is quite simple. It is not a very recent model, after all, in the convolutional neural network field. So it is a simple model, but it has worked well and efficiently, while larger models in this case would probably lead to early overfitting, as in the case of Rustnest 50. And that's all. I hope I haven't told too much.
This is very good, Niccolo. It was a very nice presentation, very good work. Any questions? Any suggestions to improve? Because now he's writing a conference paper, in fact, but I feel that because this is state of art in this area, in fact, because no one has been using machine learning before for this problem. So any good results here would be published. So,
yeah, because I see that in the physics field, they use, for example, other artificial intelligence techniques, but in this field, they don't use machine learning and artificial intelligence so much. So it is also quite easy to just apply the basic parts of machine learning to problems that are currently addressed using other methods and obtaining better results, actually.
So in fact, Niccolo, I feel that if you I mean this paper, if when it's published, it will get lots of citations because it's maybe just to try to use machine learning in different areas, in fact.
Yeah, I hope so. If they accept it, I hope so.
So what is your suggestion if we want to improve? Is there any suggestion? So my point here, Niccolo, first point for feature selection, you tried this cubic square of x1 and x2 maybe, right? So maybe you need to check this one more time. You can try to use different combinations. Maybe x1 times x2, maybe x1 square root, cubic square.
No, the square doesn't work because the square does not preserve the sign. Okay. So for the helicity, I have to take only the odd numbers.
What about interaction between features? x1 times x2, stuff like this. Is that something which you need to check?
Yes, that can be also an idea. Actually, I haven't made other attempts because to generate the images, it takes a lot of time to generate the images. It takes at least 20 minutes to generate one image. So it takes several computational days to generate them. And since the results were better than the baseline, I have just focused on the machine learning part for this reason. But of course, it will be possible to try also with other with other transformation, as
because
we have seen in the previous
uh,
slide.
we'll ask, maybe you need to check other options, also other combinations of features. So this is one point. Another point also, this is a model. You use the Google Net. Maybe you need to check maybe other models. You didn't. I mean, if you want to expand this paper into a journal paper, you need to try different models, for example, and make comparisons.
Yes,
You need
yes,
to
I agree. That part actually doesn't take a lot of time. Shouldn't take a lot of time, because actually in this case the actual machine learning part takes a few minutes in now. At the beginning it took hours and hours and hours, but because the data were not good. Now that the data are better, I can just perform the machine learning part for both the 2 and the 3 classes case in half an hour indeed, and then done in half an hour without using.
You didn't mention it was a fully connected layer. What was the structure of the fully connected? You used Google Net, but you didn't mention how the fully connected layers look like. You have 3 classes, but how many fully connected layers you have? Maybe you need to provide a graph to just have a graph describing the whole system, and maybe also you are freezing the whole model, the whole Google Net. So, but what if you try to fine tune the last layer of the Google Net? For
Actually, I used a pre-trained Google Net, so I don't think I am retraining everything. I think I am using that as the Google Net as the base, and I train on top of that.
Yeah, yes. So you have just the training the fully connected layers, but if you can train the last layer, for example, so you can try to fine tune the feature maps. You know, the last layer, the top layer which is connected to the fully connected layer. Maybe you can try it, right?
Okay. Yes.
There is a question from Saad. There is a question from Saad.
Yes, we have a question from Saad. I can present. Yes. Oh, which do you use the data points as inputs or plots images? So you have a question from Saad.
So I should have drawn maybe a flow chart about what to do. So the idea is that the simulator takes some inputs that are actually some parameters. Then the simulator generates the points that are energy, x and y. And this is the output of the simulator. And this is not the input for my network, for my model. What I do for my model actually is taking those points, drawing a plot that is that can be either the initial plot, so the one without transformations, or the one with the cubic root transformation. And I use that plot, so the transport plot, that is an image, as an input for the neural network, because the initial data points by themselves don't have information about the proximity of the points, while an image has actually, since it is a visual feature. I think this is the easiest approach. I don't know if I have answered your question.
Yeah, okay. Thank you very much, Nicolo. Any other questions? Any other questions online or here in the classroom? Any questions, Nicolo? So now Nicolo is working in a paper. Maybe he will submit it after New Year. Maybe if he has time, he can expand it into a journal paper and go for a journal instead of going to a conference. You need to add more pictures, more graphics, describe the system in more details. So just need more details, Nicolo, because you have very good results in text. And it could be very good journal paper if you don't want to waste your energy into a conference. Because when it's a journal, it will have more impact in text. And I feel it's something which can be published because it's a state of art in physics. And it's nice because it bridges the gap between machine learning and physics, and it's a new application. So I'm expecting that if this paper will be published as a journal paper, it will be highly cited. And it will be open the area for many people from physics, maybe to use machine learning in similar problems.
Yeah, because so far I see that they use machine learning in the particle physics field. For example, at CERN, they use machine learning a lot. But in other fields, they prefer, for example, Bayesian networks and things like that, but not much machine learning and computer vision. I've looked on DBLP, for example, just writing CNN and astrophysics. I think I got 3 results or less, maybe 0 results. And on Google Scholar, there are some more results, but not a lot of results, I have to say.
Maybe not needed.
In physics.
Yeah. What is the impact of this study?
Because it's hard for experts to differentiate, to classify those helicity.
One is clockwise and one is
No, but when you see this distribution, so there is big overlap in fact between the 3 classes, and sometimes it's hard for even practitioners and people and domain experts to differentiate between.
there are total 3. One is positive,
Positive, negative, and 0.
zero helicity.
Yes,
So the
yes.
main confusion is zero helicity, right?
No, because positive and 0, there is big overlap between positive and 0, and also there is big overlap between 0 and the negative.
So this problem is solved by this network.
Yes, so we can reach accuracy 94% with 0 and negative and positive when it's 2 classes. When it's 3 classes, you can achieve maybe 70. How was the accuracy in the group? Was 74 something?
77. Now it is 77%.
Along with zero helicity.
Yes. So the baseline accuracy for the baseline accuracy in Kolo from positive and negative. From where? Is there any publication?
So for positive and negative, the baseline was about 73%.
What was the model?
Sorry?
What was the model? What was the, I mean, is it a model which has been done before?
Not a model in the machine learning way of thinking. It was the Q estimator. So if you look at the actually two curves, the accuracy can be obtained by seeing the part of the area under those curves, which is not overlapped between the 2 curves. Because if you have a point that is not in the overlap area, that means that you're sure that the helicity is that one. So actually, they use different terms. So it is it's not possible to find, okay, the accuracy is 73%. They say the overlap is 50%, for example. And if the overlap is 50%, this means that with 2 curves, the average area that does not overlap is 72.5%.
This is the main contribution of the paper, so you need to focus on this. You need to compare your results with the QNet. It's called the Q estimator. So you need to, I mean, you need to stress on this point. Compare your results with the Q estimator and try to focus on that point, because this is the main contribution.
Yeah.
Also with,
and they use this Q estimator. The Q estimator basically is a formula that takes the physical meaning into account, while machine learning, of course, doesn't know about the physical meaning. It only looks at the plots. They could represent anything, actually. But this Q estimator contains some information about the energy. So the idea is that those points all have an energy. The set of points for a certain observation, for example, or a certain simulation in this case, this set is divided into 3 energy beams. I don't remember exactly how they divide into the 3 beams, but let's assume that there are 3 energy beams that goes from 0 to x, x to y, and y to z, for example, where z is the maximum energy level. They take 1 point from the first energy beam, 1 point from the second one, and 1 point for the third, and they see the helicity for those 3 points. And this is basically the Q estimate. They take the sign, and this is what the Q estimator does in practice. And they repeat this procedure for many times, which is a different approach from machine learning. So it is not exactly a model, it is a Monte Carlo simulation. They usually take 500 sets of 3 points, and they obtain the curves in this way. Because if they take 3 points at random, of course, if for example, let's assume that there is a positive helicity that is very clear. In that case, the majority of the points will be classified as positive helicity. Instead, if you have something that is less clear, then if you take 3 points at random, sometimes they will be positive, sometimes they will be negative. And so it is difficult to say, okay, there is a majority of positive points or negative points, and so on. I don't know if the idea is completely clear.
Yeah, thank you very much, Nicolo. Just keep with the paper, keep writing and improving it. And if you do more simulations and more training, you can just do it. So, but your results now, it's something very good. And I just propose that maybe at some point you can decide. Now you are writing a conference paper, but at some point you can also expand it into a journal paper.
I don't know how it works in the physics field for conferences and journals. I have to ask, actually.
We need to ask the professor from Tunisia.
Yeah.
Okay, thank you very much, Nicolo. Thank you very much for your presentation. So the next presentation will be for Masoud. I will share, I will give you. So you can share your screen now, Masoud?
Yeah, okay. How? I don't know how can I do it.
Just share screen. You have this button in the bottom called share screen.
Ah, yes.
Oh, you are from the Department of Physics, so your input, in fact, was very important to Nicolo.
Yeah, but it's different. It's for medical physics.
Mm-hmm.
Yes. Okay, my project is application of masked RCNN on breast cancer tumor segmentation. First, I explain RCNN and masked RCNN, and then I will explain my model. For this project, I used a data set of 344 raw MRI images that have been taken from 117 breast cancer patients during several months of therapy, which can show if a therapy such as chemotherapy have been effective or not. The data is gathered from Trondheim, Bergen, Oslo, and Stavanger hospitals using different MRI machines and different modalities that gives us different resolutions and different signal to noise ratios. Okay, what is RCNN? RCNN is an object detection algorithm that consists of 4 steps. First, it accepts an input image, extracting around 2,000 region proposals using an algorithm such as selective search, then extracting features from each proposal ROI using a pre-trained CNN, and finally classifying the features for each ROI using a class-specific linear SVM. Here we can see the steps we have in our CNN algorithm. Okay, so what is a selective search algorithm? It takes the place of a sliding window and image parameters, intelligently examining the input image at various scales and locations, thereby dramatically reducing the total number of proposal ROIs that will be sent to the network for classification. We can thus think of selective search as a smart sliding window and image pyramid algorithm. what are the drawbacks of the RCNN? It takes a huge amount of time to train the network, as you would have to classify 2,000 region proposals per image. It cannot be implemented real time, as it takes around 47 seconds for each test image. And also the selective search algorithm is a fixed algorithm. Therefore, no learning is happening at this stage, which could lead to the generation of bad candidate region proposals. So what is the solution? The solution is fast RCNN. In fast RCNN, instead of feeding the region proposals to the CNN, we feed the input image to the CNN to generate a convolutional feature map. From the convolutional feature map, we identify the region of proposals and warp them into squares. And by using a ROI pooling layer, we reshape them into a fixed size so that it can be fed into a fully connected layer. From the ROI feature vector, we use a softmax layer to predict the class of the proposed region and also the offset values for the bounding box. The reason fast RCNN is faster than RCNN is because you don't have to feed 2,000 region proposals to the convolutional neural network every time. Instead, the convolution operation is done only once per image and a feature map is generated from it. In faster RCNN, instead of using selective search algorithm on the feature map to identify the region proposals, a separate network is used to predict the region proposals. The predicted region proposals are then reshaped using a ROI pooling layer, which is then used to classify the image within the proposal region and predict the offset values for the bounding boxes. Here we can see the speed of these three algorithms. Left graph shows that fast RCNN is significantly faster in training and testing sessions over RCNN, where you look at the performance of the fast RCNN during testing time, including region proposals, slow down the algorithm significantly when compared to not using region proposals. Therefore, region proposals become bottlenecking faster on RCNN algorithm, affecting its performance. Also, from the graph on the right side, we can see that faster RCNN is around 10 times faster than fast RCNN. Therefore, it can even be used for real-time object detections.
So 1 minute, Masoud, please. Can you go back one slide, please?
Yes.
So if you are working with different algorithms, it will be very, very important to compare time, training time, and so go ahead, please.
Yes. Okay, all the previous algorithms are object detection algorithms that cannot be used for segmentation on the image. Therefore, by combining the faster RCNN with FCN algorithm, which is a fully convolutional network, we can do the segmentation. As we can see in the image, faster RCNN has two outputs for each candidate object, a class label and a bounding box offset. To this, we add a third branch that outputs the object mask, which is a binary mask that indicates the pixels where the object is in the bounding box, which is done by the FCN algorithm. Mask RCNN has a couple of additional improvements that makes it much more accurate than the FCN alone. So the mask RCNN model is divided into two parts: region proposal network, or RPN, to propose candidate object bounding boxes, and binary mask classifier to generate a mask for every class. The RPN is a lightweight neural network that scans the image in a sliding window fashion and finds areas that contain objects. This is a simplified view, and in practice, there are about 200,000 anchors of different sizes and aspect ratios that overlap to cover as much as the image , and choose the anchor which is the best one. For example, here we can see an example of RPN proposals that makes bounding boxes for every defined object and final detections and masks. Okay, here on the left, you can see examples of the breast MRI images. To build the data set, we should first define the classes of our images so that we have here only one class, which is tumor. Then we add the images together with annotations we have made using a manual segmentation software. Then the model extracts width and height of the boxes according to the annotation file and generates the mask for every object in the image. All the images should be segmented manually before adding to the dataset in order to annotate the tumor areas as an input for the training of the model. To do the manual segmentation and objects annotation, I used VGG Annotator, which is a web-based application. The image on the right shows an example of the manual segmentation I have used. Yes, and this slide shows the steps in mask RCNN as explained before. First, 200,000 region proposals for an image, then refinement of the bounding boxes and choosing the best one as final object detection, and finally making binary mask for segmentation of the object, which is tumor here. Then we should set the configuration of the training. For this project, I used the pre-trained weights for the mask RCNN from the COCO dataset. That means the mask RCNN model starts from COCO weights instead of random values, which help us to run the model faster and obtain good results for small datasets. And this is the results I have so far. In average, for 20 test images, the accuracy is around 85%, which is, I think, great because my data set is too small.
What is the state of art in this area, Masud?
Excuse me?
State of art, what is the state of art accuracy? You can achieve 85%. I mean, did you compare your results with the state of art?
Yeah, I compare it with the manual segmentations I have done.
Yes.
Yeah. And this is the end of my presentation. Thank you for your attention.
This is very good. Very good. We have been working in similar problem, in fact, but it was segmentation of keys. So, but this problem is so I want to see some comparison with state of art. I mean, now you can achieve 85% accuracy.
Yeah.
So what is the step? I mean, you need to check literature review and to compare your results with what other people achieved in this area.
Yes, I have checked that. There is a paper that has used UNet, which is written for medical users. The accuracy of that was 75%.
Okay.
So the accuracy is here much higher than the other one.
So what is your plan? Are you writing a publication or something?
If it's possible, yes. I don't know if it will be accepted. I don't know.
I mean, but you need when you are writing a paper in this, you are using the data sets. These data sets are public?
No, it's not public.
Okay. You have permission to use those data sets?
Yes.
Okay, because it's very, very important when you are working with images for patients. It's
Yes,
very, very important. I need to have those permissions. So,
yes.
so I guess you have data sets which is really very good, and it's and you have been using some models. You have achieved very good results compared to the state of art. So I think this these results can be published, should be published.
Okay, thank you.
Yeah. So you need to invest the time. Maybe after the exam, you need to invest the time. Maybe until after New Year, for example, if you are writing a journal or a conference paper. And
Okay.
and also, I suggest also I want people to work together. I mean, in the classroom, for example, you have many people, many PhDs, so you can work with those PhD students. People can work together and write papers together and publish together. Because
Yes.
you need help, for example, in writing. You can search for some people to help you, for example, in writing. Maybe running those models one more time, refining it, fine-tuning, hyperparameters, and so on. So you can really, because when you publish something, it's a documentation, good documentation of your work. But maybe if you didn't publish it, maybe next year someone else will get much better results, and you will not be able to publish those results. Because
Yes, that's true.
if you're working in parallel, and I mean, when you have good results, you need to publish it as soon as possible.
Yes, that's true.
Yeah. Okay, so you are based in Trondheim, right?
Yes, I'm in Trondheim.
And you will be working in your master thesis next semester.
Yes.
And it will be in the same area.
Yes.
So it's very good. I mean, good introduction to your master thesis. You have already a data set. You have your code. Just need to work in this. Try to improve your results. Try to try different models and make comparisons and try to achieve much better results. If you have early results, you can publish it as a conference paper. For example, after New Year, for example, you can find a good conference and publish early results in a conference.
Okay.
You can be working in your master thesis and you can publish maybe a journal paper by the end of the end of the spring, for example, because you will have one full semester working in this problem. So I feel that you will have enough time to fine-tune comparisons with other models, check literature review, and compare your results to the state-of-art results, and publish your results again as a journal paper. Extend this conference paper into a journal paper, for example, at the end of next spring.
Yeah. Okay. Sure.
Yeah. Any questions? Any questions online? Do you have any questions online for Masoud? No more questions? Any questions? Okay. So thank you very much, Masoud, for your nice presentation.
Thank you, Professor.
Thank you. I guess we will go to the next presenter, Chicheng. Okay. Why you are? Okay. Chicheng Ho?
Yes, here. I'm now trying to share my screen. Could you give me the right?
Yes, please. You can share your screen now. So please, I mean, we are around 35 or 36 students in this course. So I wish people work together. I mean, you can work together and publish together. So at the end of the course, if you can publish 1 or 2 papers, all people together, it would be very good production. I mean, you need to build your CV, you need to build your publication list. So try to work together. All people should work together. Even if someone is based in Trondheim, you are here in Ålesund, just work together and try to publish together, because at the end, it's you need publication. You need publication. You need to build your CV. So even if it is a little bit outside your domain of your PhD work, for example, but people can work together, publish together, because at the end it's machine learning and it's a good contribution. So it should be possible to find someone to assist you in writing, revising, checking, double check your code, maybe run your code one more time and try to modify, improve your results. So at the end you can have something published, which will be very, very good in your CV and your publications. Yes. Okay. So here we have Amir, Shakon, Mahdis, Chicheng.
Yes, so I can continue?
Yes, please.
Okay. Hello, everyone. Thanks the Nico and Masoud, so exciting presentation. But we have to go back to our boarding car topic. But I wish to introduce it in 10 minutes. And I will split my presentation into 2 parts. The first part is about the freeze second and the end of the last month, and also the recent 2 weeks process. And we have 3 persons in this group. Amir, and he is responsible for the code optimizer and also focus on the data set for the top 10 classes. And Mandis, she was worked for the whole data set and also as the reporter. And I also do some work for the top 3 data sets and also do some data set reprocessing and do some sample coding. So let's have a review about our previous phrase first. In the phrase first, we have the target dataset Stanford and also include about 16,000 images. But for the annotation, for the labeled data, it's about about the 8,000. It's over the 200 classes. As we said that we wished to classify the class model, but the problem is that there are too many classes for us. So also the result is not so good. So for the first one, we have to simplify the data set into the 2 sub data set. Also, I named it as the top 10 and also the top 3. If the method is works so well for these 2 sub data sets, so we can expand it to the whole data set. So we compare the results with the baseline CNN and also VGG16 and the inception solutions. And in this phrase, I worked mostly focused on the dropout function and also used a different optimizer and the batch sizes. As these parameters influence, you can see the result.
Before going forward, I want to say something. Yes, okay, you just mentioned it here. Yeah, sorry. I just want, if you can provide a table, how many examples per each model, for example, it would be useful. But you mentioned it already in the next slide.
Yes. First, this one, we have the top 3 classes. As you see that the 3 classes and totally have the 140 images. And also I use the /. You can use the short name or depends and works more. And also the most same, but it's a bit skewed. And the validation split is 25%. And this slide, we can see that SGD for this data set, the result is better than the original data for the optimizer. So and this is one,
Can I ask a question? Why it's so noisy here?
Okay, please. Yeah.
Why it's so noisy here? Do you know why? Why it's too noisy? I mean, the scale is too.
Because the nature of that optimization.
You mean this one? Sorry.
Yeah, this is because we use stochastic gradient descent. So in fact, we are adjusting weights example by example. So it should be noisy like this one. But if you are using mini batch optimization, for example, mini batch gradient, it will be more smooth.
Yeah.
Yes, please go ahead.
Okay. So because optimizer is not the main focus influence in our test, so only one slide. And later, you can see that if we use the baseline CNN and also with the same layers, you will find the layer on the right, only these several layers and with the parameters. And we will find that if we run it with the epoch, 30 epochs with the batch size as the 1, you can see also the different batch size influence later. But the best is to use the batch size with the 1. And we will find in the nice epoch, the result is good enough. So this slide is, you can see the different, I used the different caption with the batch sizes. If the batch size is the 1, I mark as the star. And also the later with the different solutions. For example, here, this solution is with the less parameters, only the 1/10 for the second solution. The second solution is 3 million, but the first one is 0.0 million. So it means that for the solution 1, these less features is enough for the baseline to get the good. It's not very good, but it's okay for the baseline. So it's the different layers numbers for the comparison. Also with the batch sizes, we tested from the number 1 and also to the 33. You will find the with the increase of the batch sizes and the data of the accuracy and the loss will change a bit lot. So we will find the better sizes for this baseline. So if we change it to the VGG16, the result is a bit different. And here we find that the batch size is, for example, the 4, and it's better for the result. Also with the dropout parameters. And we will find that in the middle of the batch sizes for the test set, for example, the batch size is 1 or the 32, it's not so good, but we will find the Tracy about the batch size is the 4 or the 8 is a bit bad. It's a bit better, yeah, my understanding. So if we use the dropout on the bottom line and compared to the top, we will find that if we have the dropout layer, it's better to get the to reach the higher accuracy with the same epochs. And also we tested by the inceptions. We will find that in inceptions we have to cost more time, also many trained parameters, and we will find that with the similar epoch numbers, it also can reach a higher accuracy. And also we find that the batch size is about the batch size is 8 or the 16. So yeah, also do some comparison. And in the summary, the end of the October, we have finished these 3 main methods with the different parameters from the least to the most. And also we find that the accuracy is increased a lot. But the VGG16 is a medium method, I think, balance the efficiency and the cost. So yeah, this is the first. This is the second phrase result.
So
and yeah, please.
You know, just I mean, we can see improvement from baseline CNN to inception model. Mm-hmm.
Yes.
So now
yes, we will find the. Yes.
But you need to summarize.
Can I go ahead?
You need to put
okay, please.
You need to put this results in the table.
Yeah, this way, we just to find one way to go ahead. So later we use the VGG16, for example, for the top 10 data sets. It's the later phrase I wish to introduce later. Okay. So today we will continue that the recent 2 weeks. We find that we wish to implement these methods and also to try the confusion matrix and also the key for the cross validations. Yes.
I guess those cross validation use it when you are using 3 classes because
yes. No, we not use this for the 3 classes and only the 10 classes. In this report, not include, but we have tested.
Yeah.
Okay.
The results with cross validation.
Yes, we have used the cross validation. Yeah, for both for the top 3 and also for the top 10. But in this report, only top 10.
Mm.
So now the top 10 data set and also include the top 3 classes. There are so many classes and also with the same validation split percents. And this way, we not use the cross validation, not use the cross validations, and then sorry for it's a bit miss, and also have a about the epochs 20s, and it has the good results. And then we used the fourfold cross-validation because our percent is 0.2025. So yeah, it's the fourfold. So we use this way and find that it's better if we use this way. It's the epochs with the 50 epochs, and also tested 100, but it doesn't matter because the loss is is higher overfit. So, and now we are focused on the confusion matrix. You will find that the confusion matrix, the result is not so good. So we are now focused on the to find which type is not so good. Like the similar topics. So it's a bit time consuming. So we wish to need more time to find the where's the error. So the confusion matrix is can't work. And also the this is the reference of our papers. So that's our main topic. So we wish to use the future 2 weeks where we wish to finish this project and also the final report. So that's our main topic.
We don't have a final report, so I will not get a report from you, but you can write a paper, you can write a conference paper, for example, if you feel that those results are cutting edge and useful. So you can write the report, you can find a template for maybe a conference paper or something, and you can write a conference paper if you feel that these results will be published. So this is very, very important. So if you feel that, the last two projects, Nicolo and Mas'ud, I guess they have very, very good results which can be published, in fact. These results also have, you did here a very good comparison between different models in the benchmark data sets. So you can write a conference paper, you are 3 authors, 3 people working in the project, and you can just try to make good comparisons between models, try different hyperparameters, and try to get something published from it. It will be very, very useful. Writing a conference paper, it's not a big deal, in fact, and it's easy to publish. So this paper, this work is machine vision or computer vision area. So you can search for a good conference in computer vision, and you can, or machine learning, but you need to make good comparison between different models. You need to compare between time used for training each model, number of parameters. So you need to extract very nice tables and make very good comparisons between models. So thank you very much for your time.
Okay, thank you. Yeah, we will discuss later. Yeah, and also we wish to find whether it's so good for the whole data set, because the whole data set, its runtime is so time causing that. So thank you very much. Yeah.
Thank you very much. Any questions to any questions? Any questions online? Okay, so thank you very much for the nice presentation, and thank you for your team. Do we have any other groups who want to present today? Any other groups who want to present today? So in this case, we will close here today, and we will continue working next week. Next week we will start from 8:30 with some presentations. So if you want some order, you can just send me the order, or if we just select people who are ready for next, we can decide that next week. So next week will be the last week in the course, and after that you will have 2 weeks to recap and just working in your project, and I'll just take it easy. The exam will be oral. If you want to take the exam here from the classroom, just inform me. I will be the examiner, and Saleh, he will be the censor. You can take the exam from here, you can take it online, so it's up to you, and according to the situation we are, but I will be here during the exam day. For example, the exam will be 3rd and 4th. So I will prepare a list of, I will try to make groups together also according to the project. So if we have, for example, today we have a group who are 3, so those 3 we can take the 3 together, for example. So it will be according to the project, maybe according to the order of project presentations, for example. So maybe we can start with Nicolo, Mas'ud, and after that Chicheng group, and so on. I will keep this order, for example. Okay. But if you have any problem in time, you want to select different time slot, you can just inform me and we can just try to manage to fix it for you. Yes. Yes,
Ibrahim,
Masoud?
I have a question.
Mhm.
I'm Saad. I have a question.
Yeah.
Like, are these the final presentations, or do we have any presentations after the report submission?
No. I mean, we have those presentations, and write your report as you can write a report, for example, as a conference paper template. For example, you can use IEEE template for writing your report. I want to make it easy for you, so you don't need to write again. If you have intention to write a publication, you can just do it one time in IEEE template, for example, for conference paper. So you, after presentations and after exam, you can continue working with your report, and you can submit it to a conference or journal.
Okay, but and regarding the project submission, do we need to submit the whole project, including data set as well? Because the data set is quite.
No, just the report, just the report.
Okay,
And
just the report, and the deadline is 17th, probably.
yes, 17th. We have presentations, but if you want more time, we can make it, for example, 1st of December for submitting your report. But anyway, after the presentations, I will send the list of people who will go to the exam, because all people who are presenting, they are eligible to take the oral exam.
So the requirement is to have the presentation, then you can take the oral exam.
Yeah, because I want to give people more time to work in their report, just because it's so we can make it next week or the week after, for example. I will create a folder in Blackboard so people can upload their reports. We will have only one problem when we have groups, so I will try to fix it in Blackboard so we can accept group reports, because we have groups. But because I don't know the groups, which group is doing what, so I mean, from today, for example, I know groups, which group did what. So people just need to submit their reports, and after the presentations, I will send the list to Annalisa for exam list. Okay, so you can select, for example. Yes, Mohammed.
One more thing that I see most of the, like, from today's presentation, like most of them have implemented their model from scratch, and they are doing something like comparison stuff. While on which I and Leo are working, we are doing more into the practical stuff. Like, we are trying to get use the highly advanced models out there, and we are trying to implement in different applications, for example. So that's not some sort of research, that's practical implementation. So can we prepare the report like for our own?
Yes,
or do we need to prepare it from the scratch like the others are doing?
No. It's just you have a group. Are you working alone, or you have a group?
No, I'm working with Leo. So my question was that, like you said, those who presented today, you advised them to prepare the report in the form of a conference paper, like IEEE template. But they are doing some sort of comparisons which are giving the results. But in our case, I and Leo, we are working more on the practical implementations. Like, we are trying to implement a model on the real-time detection or something like video, which is not like a research topic, but more sort of a practical implementation of already built models.
Yeah. So just, I know that you will build a demo, because Mohammed, are you traveling? Are you arriving? Do you know when you will arrive to Oslo?
I'll arrive in mid-December.
Okay.
But so I have also attended quarantine after that.
Yeah, because Mohammed is developing a demo, so you will build a demo. So just write a report in any format. I'm just proposing. I mean, there is no any formal format for any report. People who have intention to publish something, I advise them to just use maybe paper template. But other people are free to do anything. You are free to do it in any way. I accept all formats. I'm just proposing, if you have intention to submit a paper maybe after New Year. So from now, when you are writing, you can just follow, select one template, maybe it was a conference which he will publish. So maybe some of you have already in his mind which journal, which conference you will submit your paper to. So in this case, use the format directly. It will save time, just saving time. But it's up to you to select any format. I will accept all formats, and I accept all kind of work, practical work, research work, all will be accepted. So just yeah, I'm just proposing, if you have intention to submit a conference paper after New Year, for example, so just try to go to this conference and try to get its template and use its template for writing your report, just to save time, because I don't want you to redo it again after New Year, for example. You can do it from now if you have intention to write a paper. Some of you also, they are working in their specialization project, right? So for those who are working in their specialization project, I will accept also like a short version. I mean, if you are using machine learning in your specialization project, so just you can just make one report for this course and one report for your specialization project. My course here, we are working with the machine vision part, machine learning part. In your specialization project, maybe it's about the application part. It's accepted. Don't make 2 reports. So don't waste your time and don't write 2 reports. I will accept here the report which you will submit to the specialization project. But in your project, just focus on the try to make it clear the contribution to the machine learning part. But it's fine because in your specialization project, you are working in an application using machine learning. So don't write also two reports. Just save time and submit only 1 report. I will accept the report from your specialization project here as well. You don't need to make 2 reports. So for example, Shushan, for example, he is working in a project in his specialization project, but he is doing machine learning. So also if he will submit the report here, which he will submit to his specialization project, I will accept it. So just make it easy. Don't waste your time. Try to be more efficient. Don't waste time for writing things in parallel. I will accept as a project which you will submit to your special, because we have students from the second year, and in the second year they are working already in their specialization project. So I will accept as a project if it is machine learning related. So yes, okay. So thank you very much for today, and we will meet again next week. And please send me if you have any questions until next week. Next week we will start 8:30, and we will go directly into project presentation for the rest of us. Yeah.
Thank you very much.
Thank you very much. Thank you.
Goodbye.
Bye-bye. Bye-bye. Stay safe because the situation of Corona is getting more risky. Yeah. Okay. So see you next week. Bye-bye.